So in this lecture we shall be talking about the remaining properties of signals, one of which is even and odd classification. So we start with the even signal. A signal xt in continuous time domain or xn in discrete time domain is said to be an even signal if it is symmetric about the vertical axis. Mathematically, even signal satisfies the condition x of minus t is equal to xt. So in order to know whether the signal is going to be is going to be even, so we will have to check for the symmetry of the signal about the vertical axis. First of all, mathematically the other way around is to substitute the time variable by minus t and to look for the outcome. If it comes out to be equal to the original signal xt, then we say that the signal is an even signal. So qualitatively, this means that what we are doing is we are trying to change the variables, the positive by negative and the negative by positive, and are going to get the values same as that of the original signal, which means that all the negative values, all the values of x corresponding to negative variable of t will be equal to the values of x corresponding to the positive value of t. So this can only be possible if the signal is going to have values on the right side of the vertical axis same as that on the left side, and that is why we say that the signal should be symmetric about the vertical axis in order to qualify as an even signal. So this is a definition that holds for a continuous time domain, and examples are shown here. So we have a signal shown here which is symmetric about the vertical axis, and again another signal which is also symmetric about the vertical axis. While in case of a discrete time, we have the definition as x of minus n is equal to x of n. For example, the signal is also shown here, which is again symmetric about n equal to 0. If we call this as vertical axis, then we will be having the symmetry of the signal. For example, at n equal to 1, the value will be same as that on n equal to minus 1. Likewise, at the value of x at n equal to 2 will be equal to the value of x at n equal to minus 2. So we have a star here which this definition is for real valued signal. So we have complex valued signals as well. So we are giving this definition for real valued signals, and we'll talk about complex if we get time later on. In other words, if the signal is flipped about the vertical axis, that is the time axis. Sorry, this should not be. This is the it's not the time axis. Rather, let me correct this. It should rather be time origin. So if the signal is flipped about the vertical axis, that is time origin, we talk about this axis, the signal remains same. So for example, here's a small animation that shows that if the signals are flipped about the vertical axis, no matter how many times, the signal will be same. So this is a way to identify whether the signal is going to be even or not. In short, if you're going to, in other words, if you're going to reflect the signal about the y-axis, so if this is y-axis, the amplitude axis, if you're going to take the reflection about this axis, then you're going to get the same signal in case the signal is even. In case of the odd signals, they are said to be odd if they satisfy the condition for continuous time. The condition is x of minus t will be equal to minus of xt for all values of t, which means that if in case we are going to change the time variable, we are going to change the sign of the time variable, then what we are going to get is the negative of the original signal. So for example, if you look into this figure, this is an example of an odd signal. So for values of t that are negative, we have xt, the values of xt positive, and for values of positive t, we have negative values of x. And if we substitute t by minus t, so in that case the positive values of t will be replaced by negative value, and the values which were negative will now be taken as positive, will come out to be positive. So in order to make them negative, we add a sign here minus. so that the conditions are satisfied. So this is the condition for signal being odd. If this condition is met, we say that the signal is not even, rather odd. And for discrete, the same definition holds, but the representation is different for discrete time domain signals. So we have x of minus n equal to minus of xn, and the example is shown here. Odd signals is anti-symmetric about the vertical axis, so which means that they will be, if they will not be exactly symmetric about the vertical axis, rather anti-symmetric. Anti-symmetric means that you will have to first flip about the vertical axis, so the signal that you are going to get will not be the original signal, rather the reflection will be taken about the x-axis as well in order to obtain the original signal. In odd signals, there are two ways to ensure whether the signal is odd or not. The first is to flip about the origin. So what does this mean? So let me explain this through the animation. Okay, let me first discuss. If we flip about the origin, you're going to get the signal one way. The second says that if you flip about the vertical axis and then you flip about the horizontal axis, then it gives the same signal in case the signal is odd. So for example, if we have a signal here, if I, let's say, flip this, the first says to flip this about the origin. So this is the origin. If I flip this about the origin, I get the same signal. So whether I flip it about from the left side or from the right side, but it should be flipped about the origin. In that case, the signal will be same. And the second says if it is flipped about where is the cursor? Okay, never mind. The second says that if we are going to flip the signal about the vertical axis and second about the horizontal axis, so we'll be flipping this two times. So which is written here, two flips. Two flips mean that we'll be first flipping it about vertical axis, then we'll be flipping this about the horizontal axis. In that case, we are going to get the same signal. For example, if you have this signal and you flip this about the vertical axis, you get this signal, and if you flip this about the horizontal axis, you get again the same original signal as this one. So the flipping about vertical axis is also called as time reversal. Flipping about the horizontal axis is called as amplitude reversal, because in case of time reversal, we are changing the axis, x-axis, which is time axis. We are interchanging them. While in case of amplitude reversal, we are changing the amplitude axis with negative with positive and positive with negative. So this can also be seen, checked through the animation. So let me show that again. So if we are going to flip this about first about the vertical axis, we get this signal, and again if we flip this about the horizontal axis, so this is the signal that we will be getting. I guess this is clear. Moving on forward. So here are three examples of even, odd, and a signal which is neither even nor odd. So if you look into this example, the first one shown in red, this is a odd signal because we have the signal symmetric about origin. So if you flip this about origin, you're going to get the same signal. And the second example shown in blue, this signal is an even signal which can be ensured if you flip up the signal about the vertical axis, you're going to get the same signal. And the third signal, if you flip this about vertical axis, you're not going to get same signal. If you're going to flip this about the origin, the signal will not be the same as the original signal, and thus the third signal shown in orange, or the variable zt, is neither even nor odd. So let's do few examples to identify whether the signal is even or odd. So I shall be drawing this. So starting with example, so this is xt versus t. Another example, let's say you can find many examples in books. But for the sake of practice, I'm going to take few examples here, and will leave other problems on you. xt versus t. And let's take a discrete signal xn versus n. So things would have been more clear if we had used graph paper, but nevertheless. So if you look into each of these examples, so things will be very easy to identify without going into mathematics of the waveform. You simply will have to look for the symmetry of the signals about vertical axis or origin. So if you look into the first example, this particular waveform is symmetric about the vertical axis, and thus this is an even signal. So for checking whether the signal is even or odd, you will have to simply look for its symmetry about vertical axis or origin respectively. And this signal is symmetric, not symmetric about vertical axis, rather symmetric about origin. So if you're going to flip this about the origin, or second, if you perform two flips, one about the vertical axis and second about the horizontal axis, so in that case you're going to get the same signal, and thus this signal qualifies as odd. The third one is again symmetric about origin, and thus this is again an odd signal. The fourth one is symmetric about the vertical axis. This is even, an even signal. This fifth one, if you look into the graph and you try to flip this about vertical axis, so if you flip this about vertical axis, the signal will be something like this. And if you flip this about origin, so flipping this about the origin will not give the same signal. Or if you perform two flip, if in case if it is difficult to look, if you difficult to flip about the origin, you can flip this about the vertical axis as well as horizontal axis. So if you flip this about the vertical axis, you're going to get the signal like this, and if you flip this about the horizontal axis, this signal, so then you will be getting a signal something like this, which is not neither even nor odd. So you can write it's neither even nor odd. And the last case, if you look, this signal is again symmetric about origin, and thus it qualifies as an odd signal. So if you still feel any doubt in identifying the even and odd signal, you can ask me questions on Google Classroom, or next time when I take live class, or you can post question or email me. So now we move forward towards the even and odd decomposition. So what we are going to do here is we are going to decompose the signal, any arbitrary signal xt, into its even and odd component. So we will be bifurcating, or we will be first of all showing it that a signal can be divided into two components. One will be the even component or even part of it, the other will be odd. So let the signal xt be expressed as the sum of even and odd components as xt is equal to xe plus xo, function of t. Xe stands for even signal, x of o stands for odd signal, and let's call this equation as 1. Now since in an even signal, the property for it is that even signal, if you're going to change the time, if you're going to substitute the time by a negative time, so x even of minus t will be xet, while in case of odd signal, the property that holds there is xo of minus t is minus of xot. So this is the property of odd signal. So now if we substitute t equal to minus t in equation 1, so substituting, replacing this t by minus t, what we get is xe of minus t plus xo of minus t. And from these properties, xe of minus t is equal to xet, so we write this here simply as xe, and x of minus t is minus xo. So the minus xo is missed here, so let me correct this again. So this is the correct form. So x of minus t can be written as xet minus xot, and let's call this equation as 2. So now we can obtain the expressions corresponding to the even and odd components, so using equation 1 and 2. So in order, if we add equation 1 and 2, so we eliminate this part xot and xot, and what we are left with is xt plus x of minus t will be equal to 2 times xe, and xe will further be written as x plus x of minus t, xt plus x of minus t divided by 2. Likewise, if we subtract equation 1 and 2, we can then obtain the relation for the odd component of the signal as x of t minus x of minus t divided by 2. So these are the two expressions that can be used in order to obtain the even and odd components of any arbitrary signal xt. For example, shown below are the components, the even and odd of ft. So if this is a signal ft, this can be decomposed into its even component shown here and the odd component shown here, and if this even and odd, they are added together, so what we get is the original signal ft. So here are a few examples to draw the even and odd decomposition of the given signal. So let me do this for you, so things will be easy, and I suggest that you go through other examples from the books. So let me redraw the first example again. xt versus t. One minus 1, and the amplitude, the maximum amplitude for the signal is 1. Now we can obtain the even and odd decomposition mathematically as well as graphically. So since we obtained the equations of the components of even and odd mathematically, so let us first try to obtain this mathematically. So we'll be expressing the relation for xt mathematically from the graph given. So if you look into the graph, we have the signal is starting as a ramp signal at t equal to -1, and the slope of this ramp is half. So because at a difference of one step from -1 to 0, we have this point which is 0.5, which means that the slope of the line is half. So the ramp signal will be having a half slope, and this will be positive, and will be starting at t equal to -1. Then since the ramp is supposed to be brought to 0 at t equal to +1, so there must be another signal that should be added to it. So this can only be possible if we somehow get rid of the slope. So this can be done if we add a negative half slope which starts at t equal to 1. So this is going to get rid of the slope, and again we will have to bring, because if we add this signal, then what we are going to get is a straight line at this particular point having magnitude 1. So in order to get rid of this one, we'll add another signal minus u t minus 1, which has a magnitude of 1, and will eliminate the magnitude 1 that we would have get when we add these two signals. So this is the required mathematical expression, and in order to decompose the signal into even and odd, so we know that the even component is given as x of t plus x of minus t divided by 2. So we simply will have to substitute the values here. Now we have half of r t plus 1 minus half of rt minus 1 minus u t minus 1 plus, again we have x of minus c, so all the values of t will be substituted from negative, like half of r minus t minus 1, sorry, minus t plus 1, and we have minus half r of minus t minus 1 minus u of minus t minus 1, and this all divided by 2. Or let us try to do this with a simpler approach, because this way things would have become difficult, though the original graph can be drawn for the even component of x using these expressions, but things are getting difficult here. So let me make this problem easier using graphical approach. So graphical approach will make much more easier. So we have the even component of x given as xt plus x of minus t divided by 2. Xt is given here. We simply will have to draw x of minus t and add them together. So x of minus t is what? Is the signal that is reversed about the vertical axis in this manner. So they should be exactly identical, flipped about the vertical axis. One minus 1 1. Now if we add these two signals, in order to obtain the even component, we'll be adding these two signals xt and x of minus t. So if you look at the points x of minus 1. Let us try to add these point to point. So at t equal to minus 1, we have this value as 0, this as 1. So let them add, and let's say the resultant signal is drawn below. At minus 1, if we add the 2 points, what we get is 1. Let's say this is 1. At t equal to 0, this is 0.5 and this is 0.5. So the resultant at t equal to 0 will be 1. At t equal to plus 1, this is 1, this is 0. So 1 plus 0 will lead to 1. Again 1. One minus 1. So we are for sure that we are going to get these 3 points at minus 1, 0 and 1. And we can try to conclude, since we have a slope of here as 0.5, the slope of here is 0.5, so 0.5 slope plus 0.5 slope, sorry, this is minus 0.5, this is plus 0.5, this is minus 0.5. So the slope of the line that we will be getting as a resultant after adding them will have slope 0, which makes that the line will be having 0 slope and passing through this point. So this is the required waveform of the sum of these two signals, and the magnitude of this is 1, while the even component should have an amplitude which is half of their sum, which means that the even component will look something like this. Xe, of course function of time, and will be having an amplitude half like this. So this is the required even component of the given signal. Now in order to obtain the odd component, so by definition odd component xot is x of t minus x of minus t divided by 2. So now we'll have to subtract this value from this. So let us try to subtract it. Xt minus x of minus t, and let's see how the graph looks like. So now if you look into the value of xt at t equal to minus 1 and x of minus t at t equal to minus 1, so let's say we have this xt, we draw minus x of minus t, so this could be much easier. So minus of, instead of subtracting these two graph, let's say we are going to add x of t with minus of x of minus t. So minus of x of minus t will be the flipped version about the horizontal axis, about the time axis, like this. So it's easier to add the signals rather than to subtract it. So that is why we have taken this minus sign, and we incorporated this minus sign with the signal and obtained the signal minus of x. So addition is easier. So now when we add these two signals, what we get is so if you look at t equal to minus 1, this is 0, this is minus 1. So 0 plus minus 1 is minus 1. If you look into this point at t equal to 0, this is plus 0.5 while this is minus 0.5. So the point that we are going to get at t equal to 0 is 0. At t equal to plus 1, we have this value as 1, this value as 0. So the value that we are going to get at t equal to 1 is 1. Likewise, if you see that the slope of this line is plus 0.5 and of this line is plus 0.5, so the total net slope after adding two slopes of 0.5 will be 1. So which means that you will be drawing the line which will be intersecting these 3 points and will be having slope 1. So this is minus 1, this is minus 1, this is 1, and this is 1. So if you draw this line will have a slope of 1. Again, this line has a slope of 1, and the final answer for the even component is this. So sorry, odd component. we were drawing the odd component, and thus the required answer is -1 having a magnitude -1 plus 1 magnitude at t equal to 1. So these are the even and odd components of the given signal xt. So things are easier in some cases if you use direct approach or graphical approach instead of the mathematics. If you use mathematics, you will be obtaining the same answers, but thing will be a bit difficult. Now we look for the second question. So the second question says x of t is equal to cos t plus sin t minus cos t sin t. So we are required to obtain the even and odd component of it. So let me write the question again. X of t is equal to cos of t plus sin of t minus cos t sin t. So this is again mathematical representation. So instead of, now this particular question will be difficult to solve using graphical approaches. So you'll have to yourself identify whether to use graphical approach or mathematical approach, because you know the mathematics pretty well about the cos and sine of relations, and that is why I suggest that you go you solve this question by using mathematics. So the even component of this signal is x of t plus x of minus t divided by 2, while x of t is given as cos t plus sin t. So let me substitute this: cos t plus sin t minus cos t sin t. Now x of minus t, so let me write the values of x of minus t, can be expressed as cos of minus t plus sin of minus t minus cos of minus t sin of minus t. So cos of minus t is cos t. Again, this is an even signal. Sin of minus t is an odd signal. So you can simply look into the signals by drawing. So if you draw the function of cos, so the signal is something like this, and this is symmetric about the vertical axis, cos function. While if you look into the sine function, this is something like this, and this is symmetric about the origin, and that is why it is an odd signal. So cos of minus t will be cos t, while sin of minus t will be minus sin t. Again, cos of minus t is plus cos t, while sin of minus t is minus sin t, so minus minus plus. So this is the value for x of minus t. If we substitute here, this is plus cos of t minus sin of t plus cos t sin t divided by 2. So now what we are left with is, so this is cancelled out, this cancelled out, so we are left with this 2 cos t divided by 2, and in other words we get this as simply as cos t. So the even component of the given signal is cos t. Likewise, we can find the odd component. So the odd component will be x ot xt minus x of minus t divided by 2. So now what we're going to get here is cos t plus sin t minus cos t sin t minus of x of minus t is cos t minus minus plus sin t minus cos t sin t divided by 2. So now this term cancels out, then we have the remaining terms as sin t this can be written as 2 sin t, or 2 cancels out, so we sine t minus 2 and 2 again cancel out, cos t sine t, and this can further be simplified and written as sine t 1 minus cos t. So this is the required answer for the second question, and let me do the third one, which is a discrete representation of the system. So because we have not yet touched any discrete signal, so it's important to do this so you can solve any discrete signals yourself later. So let us write the signal for the discrete time, which is x of n equal to minus 2, 1, 2, minus 1 and 3, corresponding to the values n equal to minus 2, minus 1, 0, 1, 2. So this series for xn appears at the values like n equal to minus 2, we have x of n minus 2. At n equal to minus 1, the value of x is 1. At n equal to 0, the value of x is 2, and so on. So this is a way of representing the discrete time domain signal. There is another way of representing discrete time domain signal, so that is simply by showing an arrow. So if you had an arrow written below the value, let's say this arrow indicates that this value appears at the origin at n equal to 0, while on the left side of this arrow corresponds to the negative values of n, and on the right side of this arrow corresponds to the values appearing at positive values of n. So this is a simpler way to represent any discrete time signal. So now we are required to find the even and odd components of this xn. So again, using the definition of even signal for discrete time says that x of n plus x of minus n divided by 2 by definition. So x of n is straightforward written there, x of minus n. So what does that mean, x of minus n? So let me write the values of n again, minus 2, minus 1, 0, 1, 2. So now I have written the series of n here. Later on I might be switching and representing the series of x by using arrows instead of writing n in this manner. Okay, one thing I forgot. So you can draw the signal as well. So if you draw xn versus n, xn versus n. So at n equal to 0, you have value as 2. This is 2. And at n equal to minus 1, you have value as 1. At n equal to minus 2, you have value as minus 2. At n equal to 1, you have value as minus 1. At n equal to 2, you have value as plus 3. So this is how discrete signal would look like. And now x of minus n can be obtained by substituting the values of n as negative. For example, if you're going to substitute the value of n of minus 2 here, so minus of minus 2 will give you x of 2. So by relation, x of 2 is 3. So you have 3 here. Now if you substitute in place of n minus 1, so minus of minus 1 is plus 1, while x of 1 is minus 1. And if you substitute n equal to 0 here, so x of 0 is 2. Now again, if you substitute n equal to plus 1 here, so you get x of minus 1, and x of minus 1 is 1. If you substitute n equal to plus 2, so minus of plus 2 is minus 2, and x of minus 2 is minus 2. So in fact, what you did is you have reversed it about the time axis to obtain my x of minus n. So this is what we had been doing in our previous slides. Now in order to obtain the even component, we'll simply will have to add x of n with x of minus n. So the even component comes out to be equal to minus 2 plus 3 is 1 plus 1, 1 plus minus 1 is 0, 2 and 2 is 4, minus 1 and 1 is 0, 3 and minus 2 is 1, and this will be divided by 2. Each of these values will be divided by 2. So you get this signal as 0.5, the first value, 0, 2, 0, 0.5. So this is the even component of the given signal. Likewise, we can obtain the odd component by simply subtracting them. So odd component can be obtained by subtracting xn with x of minus n. So if you subtract this xn, minus 2 minus 3 divided by 2, this is minus 5 divided by 2, which comes out to be minus 2.5. Minus 2.5. This next value is 1 minus 1 is 2, divided by 2 is 1. 2 minus 2 is 0, divided by 2 is 0. Minus 1 is minus 2 divided by 2 is minus 1. 3 minus of minus 2 is 5, divided by 2 is 2.5. So this is the required odd decomposition, odd component of the given signal. So if you still have any doubt how to decompose signals, so you can ask me later on. Now we talk about the properties of even and odd signal. So let me rub this. So the properties, there are few properties associated with even and odd representation of any signal. So let me write these properties. The properties are that if you in the first property there are certain sub properties. The first of which is if you multiply two signal, one of which is even, the other is odd, then in that case the resultant will be an odd signal. In case if you multiply two odd signals, then the resultant will be an even signal. And in case if you multiply two even signals, the resultant will be an even signal. And in case if you multiply an even with an odd, so this had been taken. So what other combination is possible? Even, odd, 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 even, even. Fine. So odd and even multiplication will also result in an odd signal. That has been taken above in the first sub property. The second says that if xt is even, suppose we have a signal which is even, then if you integrate this from a range minus infinity to plus infinity, then you are going to get, you can represent the signal, because okay, let me first write this, 0 to infinity 2 times xt dt. So I guess if you clearly understand the definition of even signal, so you will be able to get what is written here. So since if you talk about the left part of the range of t, that is from minus infinity to 0, so for all negative values of t from minus infinity to 0, if you substitute the value of t in xt, you will get the original signal xt. Since the even signal are symmetric about the vertical axis, which means for all negative values of t, the values of x will be same as that of the positive values of t, and thus we can, instead of writing in this manner, we can say that the value will be equal to 2 times from 0 to infinity xt dt. And then the third property says that if xt is odd, then minus infinity to plus infinity xt dt will be equal to 0. The reason for this is because from minus infinity to 0 the x will be negative, and from 0 to infinity it will be positive, so negative and positive will result to 0. And again we have few more properties, so let me rub this. The fourth property that says if xt is going to be even, then its derivative is odd. So this can be proved very well, and in order to remember whether this is going to be odd or even, so you can take an example of sine or cos waves. So since cos is a even signal, cos t, if you take the derivative of cos, what you get is a sine signal, and sine is an odd signal. So in order to remember the fourth property, you can use example like cos and sine. Likewise, the fifth property says that if xt is odd, so using that same way of learning using sine and cos, you can conclude that the derivative of xt will be even. So this is enough with the properties of even and odd, and the next topic is periodic and aperiodic signal. So we'll be talking about this in the next lecture. So if you have any questions related to this lecture or any lecture that had been taken in the past, you can ask me or post your questions or email me on the ID given below.